Okay, we will continue with parts per million, ppm. So by definition, ppm is weight of substance over weight of solution times 10 to the power of 6. Okay, because million have 6 digits. Okay, so ppm, parts per million, also equivalent to milligram per liter or microgram per mil. Okay, so the concentration in ppm is weight of the substance divided with weight of solution times 10 power of 6. Okay, that will be equivalent to ppm. Okay, for dilute aqueous solution, 1 ppm is actually referring to 1 milligram per liter. Means 1 milligram of substance in 1 liter of solution. Okay, go back to the previous slide just now. Okay, uh, so ppm is equivalent to milligram per liter or microgram per mil. Moving on to next one, which is parts per billion, ppb. So by definition, it means weight of the substance divided with weight of solution times 10 power of 9. Okay, billion because of 9 digit. So parts per billion also equivalent to microgram per liter. Okay, or nanogram per mil. Okay, so nanogram of solute per gram of solution for aqueous solution. Okay, so let us see one example here with regards to part per thousand and parts per million. So just now I only mentioned parts per million and parts per billion. So parts per thousand means, okay, 10 power of 3 because 1000 will have 3 digits of 0. Okay. Okay, a sample weighing 1.3535 gram contains 0.4701 gram of iron. So calculate the percentage of iron in the sample. Next, calculate the content of iron in parts per thousand and parts per million. Now, what the question is requesting from you is percentage of iron, okay, and also parts per thousand of iron, and also parts per million of iron. So how are we going to solve this question? Okay, look at the information given. Okay, the first one is sample weight. Then look at the iron content. Okay, so let us solve the first question, which is percentage of iron in the sample. Okay, so means percentage here is times 100. Okay, so what by definition is this is the amount of substance, which is 0.4701 gram. This one is 1.3535 gram, so we can cross the similar unit gram here. So you will get the answer in percentage. Okay, how to solve parts per thousand and parts per million? Also follow the definition. Okay, so definition is 1000, so this one is replaced by 10 power of 3. This one replaced with 10 power of 6. Okay, now let's see the answer. Okay, so this is for the percentage just now. Okay, okay, so you solve here. Okay, the percentage. Okay, calculate on your own. Okay, parts per thousand. Okay, 10 power of 3 Okay, so 347.3 parts per thousand. Don't forget to write the unit. Okay, parts per million. Okay, 10 power of 6. So we get times 10 power of 5 ppm. Now try to calculate for parts per billion. Okay. Next we go to percent concentration or parts per 100. Okay, like the previous example just now, the first part of the question is asking for the percent concentration. Okay, so weight percent is referring to weight over weight, means mass of the solute over mass of the solution times 100 because it's percent. Okay, volume percent is volume over volume, so volume of solute over volume of solution times 100. Weight volume percent is mass of solute over volume of solute times 100%. Okay, let us look at example 9 here. What is the weight over weight percent of an aqueous ammonia solution at 14.3 molar with density 0.9 gram per mil, which is also equivalent to 900 gram per liter. So we convert this. So in 1 mil, we have 0.9 gram. So what if we, what is the amount if the volume is 1000 mil or equivalent to 1 liter? Okay, so you do the, yeah, okay, cross multiplication. Okay, so we get 900, okay, gram. Alright, so how to solve this question? Okay, so first find the molar mass. Molar mass of molecular weight of ammonia. Okay, so refer to periodic table. Nitrogen is 14 gram per mole. Hydrogen is 1 gram per mole. So because there are 3 hydrogen here, so total is 17 gram per mole. Now why we need to find molar mass? Because we need to find mole. Okay, so remember the one of the formula I asked you to memorize. Okay, so to find N, you need molar mass also. Okay, N, number of mole is mass over molar mass. Okay, molarity is N divided by volume. Okay, okay, to find mole, so we have 14.3 molar here. Okay, molarity. Okay, so we need to find N here. Okay, so molarity is given. Okay, so the volume here is in liter. Okay, liter. Yeah, okay, so 1 liter. So the number of mole is 14.3 mole. Okay, so we use number of mole here, and molar mass. We should be able to find mass. Okay, so now number of mole 14.3 times molar mass, which is 17 gram per mole, we will end up getting mass. Okay, once we get mass, we can solve this question. Weight over weight percent. Okay, so this is weight. Okay, so use the density given just now, okay, and then convert it to the relevant unit, which is 900 gram. Okay, so In step 3 just now, the mass that we obtained, mass of the solute, substitute it here. Okay, mass of the solution, which is the mass of the 1 liter ammonia, we substitute here, times by 100, we should get 27 weight over weight percent. Okay. Okay, example 10 is the other way around of example 9 just now. So if you notice now, the question is asking for you to find the molar concentration. Okay, molar concentration, molarity, given the density and also the weight over weight percent, 27. Okay. Okay, similarly, okay, we find the molar mass of ammonia, which is 17 gram per mole. Okay, and then step 2 is to find mass of ammonia. And to find mass of ammonia, okay, we go back to the formula that you need to memorize, in which N is mass over molar mass. Another one is number of mole, molarity times volume. Okay, and we need to find this. Okay, molar mass or mass of ammonia. Okay, so mass here is equivalent to number of mole times molar mass, and number of moles here can be found from molarity times volume, and this is the unknown question that we need to solve. Okay, so that's how you see here CV. Okay, V is the volume, C is the concentration of ammonia. Okay, times molar mass. So we leave it as it is first. Okay, moving on to step 3. Okay, we need to find the mass of 1 liter solution. Remember, this represent mass of solution, this represent mass of the solute, and we need to find this first. Okay, since we cannot solve this yet. Okay, so we need to find this. Okay, so how to find this? Okay, so in 1 liter of solution, okay, to find the mass is volume times density. Okay, so this is another formula. Density is mass over volume. Okay, the third formula that you need to memorize. So we want to find this mass of the solution, so the density times volume. Okay, volume of 1 liter, density here we convert it to 900 gram per liter, so that we can cross this unit liter, and we end up getting mass, which is 900 gram. Okay, next we use that 900 gram information. We use the weight over weight percent here to find mass of the solute. Okay, so therefore from this question we can solve and find mass of the solute. Okay, which is 243 gram. Okay, so once we get 243 gram, okay, so that is referring to the mass. Okay, so to find molarity here, okay, go back to the step 2 just now. Okay, step 2, which is mass MV times molar mass. Okay, so we have obtained this just now, which is 243 gram. Okay, this is the information we want to find out. Volume, okay, let's say 1 liter. Okay, molar mass is 17 gram per mole. Okay, So bring this here. Okay, so we should be able to solve molarity in 1 liter, which is 14.3 mole per liter. Okay. Okay, example 11 is volume over volume. So what is the volume over volume percent of ethanol in a solution prepared by mixing 5 ml of ethanol with enough water to give 1 liter of solution? Okay, so how to solve this question? Okay, by definition, okay, volume over volume percent means volume of the solute over volume of solution times 100%. Okay, so we have the volume of solute here 5 ml. We have volume of solution 1 liter. Okay, note that the unit is different here, so therefore we have to convert the unit to similar unit. So you can convert mil to liter, or you can convert this liter to mil. Either way around, either way is correct. Okay, as long as both units are the same. Okay, so we convert, let's say we convert this 5 ml into liter, so it becomes 0.0005 liter. Okay, over 1 liter times 100, so we get 0.5 volume over volume percent. So usage of percent concentration varies. Okay, of commercial aqueous reagents usually sold in weight percent. Okay, weight over weight percent. So when you look around in the lab, okay, one of the example is 37% hydrochloric acid. So this actually means 37 gram of HCl solute in 100 gram of solution. Okay, so normally it refers to weight over weight percent. Okay, and to convert that 37% to molarity, we need the information on density like we solved example 9 and 10 just now. Okay, so we need to find the density of hydrochloric acid to find the molarity. So this is the common confusion over concentration units. For example, weight over volume and volume over volume. So let us compare 5% weight over volume ethanol to 5% volume over volume ethanol. It looks the same, but it is not in terms of strength. Now, the first one is 5% weight over volume. So by definition, it means 5 gram of the ethanol in mass over 100 ml of solution times 100. Okay, so what we have to convert this into molarity. That is how strength of the solution can be expressed. Okay, so how we do this? Okay, so this is the mass of the solute. Okay, so to find number of mole, number of mole, we need mass and molar mass information. So we need to convert it to number of mole first. Okay, because molarity is referring to N over volume. So we need this information first, number of mole. Okay, so we had the information on mass, which is 5 gram, and how to find molar mass. Okay, we have to look for predictable. Now the formula for ethanol is CH3 CH2 OH. Okay, so this is the formula of ethanol. So the molar mass, molar atomic mass for carbon is 12, hydrogen is 1, okay, oxygen is 16. So 12 plus 3 plus 12 plus 2 plus 16 plus 1 will give you 46 gram per mole here. So mass divide with molar mass, we get number of mole, which is 0.109 mole of ethanol, okay, in 100 ml of solution here. Okay, so we leave it as it is first. Okay, moving on to next, 5% volume over volume. So by definition, it means 5 ml of ethanol solute in 100 ml of solution times 100. Now for this case, we need the information on density. Okay, remember just now the third formula that you need to memorize is density, mass over volume. Okay, so the density of ethanol is 0.7893 gram per mil. Okay, so we are given the we know the volume of the solute, which is 5 mil. Okay, leave the unit of density as it is because we just leave the volume in mil. Okay, so we need to find number of mole. Okay, we need to find number of mole. So volume times density, volume times density, we get mass. Okay, mass. Okay, so mass divide with molar mass, we get number of mole. So here is how we do it. Okay, density times volume divide with molar mass. So we get 0.0859. So this one can cross. So we get mole. Okay, 0.0859 mole per 100 ml of solution. So we compare this one and this one. So the first one is 0.109 mole. Second one is 0.0859. You see the difference in terms of the strength. So 5% weight over volume is actually stronger compared to 5% volume over volume. Okay, and the difference here is 21.2%. Okay. Okay, next we look at stoichiometric calculation and the factor label method. So I have explained to you what stoichiometric is. Okay, stoichiometric means you must have a balanced equation of the reaction, okay, in the reactant side and the product side. Okay, and then we compute all the molar mass, okay, referring to periodic table. And then we write down the given and unknown quantities, and then we set up conversion factor using the stoichiometric coefficient in the balance equation. Okay, example. Okay, suppose 5 gram of hydrogen gas. Okay, hydrogen gas reacts with excess oxygen gas, okay, to produce water, H2O. Okay, so 5 gram here. Okay, this is where we write down, okay, the given and unknown. Okay, 5 gram react with excess to produce water. Okay, so how many grams of oxygen, okay, grams of oxygen required, how many grams of water can be made? Okay, so we have write down all the given and unknown quantities. So make sure the equation is balanced. Okay, is it balanced? No, it's not, because we have 2 hydrogen in the reactant side, 2 hydrogen in the product side, but only 1 oxygen in the product side. In the reactant we have 2. So what do we need to do is balance this equation. So we put 2 here, 2 here. So we have 2 oxygen, but hydrogen now become 4, but here we have 2, so we put 2 here. So it become balanced now. Once it's balanced, then we can proceed, okay, using this conversion factor. Okay, so we need to find how much of the oxygen consumed, although it's provided in excess, but this is the limiting factor. Only 4 gram is applied. Okay, so what is the amount of oxygen here required to react with this 4 gram of hydrogen? Okay, so how to find this? Okay, go back to the formula that you need to memorize. Okay, which is number of mole mass over molar mass. We need to find this information here. Okay, and we need to find this and also this. How to find molar mass? Refer to the periodic table. Oxygen is 16, so 16 times 2, we get 32 gram per mole. How to find N? So N can be found from here due to the stoichiometric coefficient factor, conversion factor. Okay, so N mass over molar mass for hydrogen. Mass is 4 gram. Molar mass is 2 here. Okay, 2 gram per mole. Okay, so we have 2 here. 2 mole. Okay, now look at the stoichiometric. So this is the stoichiometric. 2 mole of hydrogen react with 1 mole of oxygen. Okay, so 2 mole of hydrogen react with 1 mole. Okay, so based on calculation, here is 2 mole. Okay, number of mole, 2 mole. So what is mole of this? Okay, so use the cross multiplication, so this is become x. So 2 times 1 divide with 2, so we get 1 mole. So here is 1, so therefore mass of oxygen is 32 gram. Okay, so we solve, we do the same approach for water. Okay, stoichiometric relationship. 2 mole of hydrogen produce 2 mole of water. Now let's see the answer. Okay, so this is the answer for oxygen. This is the answer for water. Okay, the same approach. Okay, so this is the summary. Okay, so we use the coefficient from balancing equation to solve moles between reactant and also between reactants and also product. Okay, using molar mass, we can find the mass. Okay, mass of substance. Okay, next is preparing solution. Okay, so how to prepare solution? Okay, especially from pure solid. Okay, pure solid. So the first thing that we need to do is calculate the amount of the solid required first. What is the amount in terms of mass? Okay, once we have calculated, then we weigh. Okay, weigh out the solid. Okay, once we out the solid, then we place this solid into appropriate volumetric flask. Now to prepare solution, the glassware is always volumetric flask, not beaker, not Endler-Meyer flask, not measuring cylinder, but volumetric flask. Then we fill the flask to half full with water, and then we mix. Okay, we shake. Okay, we shake the flask, and then we fill to the mark with water, and then we invert. Okay, up and down. Okay, to make sure the solution is homogeneous. Okay. Next is dilution. So many laboratory chemicals such as acids are purchased as concentrated solution. Okay, so these are called stock solution. Like just now, in the previous example, 37 weight over weight percent of HCl. So this normally in the form of solution. Okay, solution. So to do dilution, okay, we take certain amount from this stock solution and then dilute with water. Okay. But first we need to find this in terms of molarity. Then um, we can find out the volume needed. Okay, based on the molarity of this and the molarity of solution or dilute solution that we want to prepare. And here comes the fourth formula that you need to memorize, which is M1V1, M2V2. Okay, dilution formula. So M1V1 is actually representing number of mole. Okay, remember the first formula? N is MV. Okay, so number of mole of solute before dilution will be the same as number of solute after the dilution. For example, you have 53.4 ml of 1.5 molar solution of sodium chloride in hand, but you need 0.8 molar, which is a diluted version. How much of 0.8 molar can you make from this 53.4 ml? Okay, so we use this M1V1, M2V2 formula. So M1 is 1.5. Okay, V1 is 53.4. How much of 0.2 that we can prepare here? Okay, so we solve V2. So here's the um, the option. Okay, you can keep the volume in milliliter provided both sides are the same milliliter in milliliter unit, or you can also convert this in molar. Okay, also no problem. You convert it into liter, sorry. So V2 is 100 ml. So next, a stock solution of 1 molar sodium chloride is available. How many ml of this stock solution needed to make 100 ml of 0.75 molar solution? Okay, so again M1V1, M2V2. How many ml needed to make? So means to make 0.75 ml, which is 100 ml in volume. So here is 1 molar. So how much we need to take from this solution? This one. So V1 here is 75 ml. So by definition, M1V1 is mole of solute before dilution, M2V2 mole of solute after the dilution. So although the number of mole of solute does not change, the volume will normally change based on the question example that that we calculate just now. Okay, so the concentration of the solution will change since the volume also change. Okay, moles will be the same. Okay, example 12, you have 50 ml of 3 molar of sodium hydroxide and you want 0.5 molar of sodium hydroxide. So what do you do? Okay, initially you have 50 ml of 3 molar sodium hydroxide in hand, but you only want to prepare 0.5 molar. So what do we do? Okay, again M1V1, M2V2. Okay, so 3, 50. Here 0.5 V2. So what is V2? Okay. Okay. So V2 here is 300 mil. Okay. So you already have 50 mil. Okay, you already have 50 mil. Okay, but the total volume has to be 300 mil. So means you have to top up another 250 mil of water so that you get 0.5 molar. Okay. So this is the solution to example 12. Okay. Add 250 ml to that 50 ml of stock solution so that we get 0.5 molar of 300 ml sodium hydroxide solution. Okay, next is how to make dilute solution. Okay, so dilution also will need volumetric flask to prepare the solution, but to transfer the solution from stock to that new volumetric flask, we need to use pipette. Okay, so pipette is used to deliver solution from the stock to the new volumetric flask, not measuring cylinder, not beaker. Okay, we have to use pipette so that we will prepare accurate concentration. Okay, because when you use burette or when you use measuring cylinder or when you use beaker, the error is bigger, larger. Okay, so we pipette the volume of the concentrated solution to a new volumetric flask, and then we add solvent to the line of the neck or the mark of the new flask, and then we invert so that it mix well. Okay, for example 13, the information is all written there. So I want you to do this as your attendance exercise. Okay, so solution stoichiometry. Okay, remember reaction will occur on a mole to mole basis. And for pure reactant, we measure the reactant using mass. For reactant that are added to a reaction as aqueous solution, we measure the reactant using volume. Okay, so this is the summary. Okay, so if we have substance A and B, doesn't matter is between two reactants or one is reactant, another one is product. But in terms of molar ratio, is always stoichiometry, based on stoichiometry. Okay, and then if we have the information on mole and molar mass, we can find grams. And if we have molarity information, and mole, we can always find volume. Or if we have molarity and volume, we can always find mole. Okay, and then we can relate substance A and substance B based on their molar ratio. Okay, the stoichiometric ratio just now, 1 molar react with 2 molar, producing 2 molar. Okay, so this is the stoichiometric molar ratio. Okay, example 14. 25 ml of 2.5 molar of sodium hydroxide needed to neutralize or to react completely with a solution of phosphoric acid. How many moles of phosphoric acid were present in the solution? Now, given the balanced chemical equation here, sodium hydroxide react with phosphoric acid to produce sodium phosphate and also water. Okay, so double check to make sure balance both side, reactant side and product side. So here 3 sodium, 3, 1, 1, 4, 5, 6, 7. So 4, 5, 6, 7. Okay. Phosphorus 1, 1. Okay. Hydrogen 6. Here 3, 4, 5, 6. Okay, so balance. So what are the information given? 25 ml of 2.5 molar sodium hydroxide react with phosphoric acid. How many mole of phosphoric acid present in the solution? So what is number of mole here? Okay. So these are the information given. So we have volume, we have molarity. So what information can we get from here? We can get number of mole. Okay, N is M times V. So M 2.5 volume converted to liter, 25 divided with 1000. So we get number of mole. Once we get number of mole, which is 0.0625 mole. Use the stoichiometry. So 3 mole of sodium hydroxide react with 1 mole of phosphoric acid. Okay, so 3 and 1. So we have 0.0625 mole. So how many mole of phosphoric acid react with this? So again we do the multiplication. Okay, cross multiplication. So 0.625 divide with 3. Divide with 3. So we get 0.0208333 and so on mole. So this is the number of mole for phosphoric acid. Okay, here. So we have solved that. Okay, what do we do next? Okay, so this is the approach in order for us to get that 0.0208. So here's the answer. Okay. So titrimetry. So titrimetry will refer to a group of analytical techniques which takes advantage of titers or concentrations of solutions. So the word titer is also used to denote equivalence or the amount of solution required to complete a chemical reaction. So titrimetry often refers to the use of some volume of a solution of known concentration to determine the quantity of an analyte. Okay, but there are some variation on the use of the term. So I'm sure you are very familiar with titration. So this is example of determination of hydrochloric concentration by titration using sodium hydroxide. So first of all, we pipette. So this is pipette. Okay, 20 ml of acid solution, hydrochloric acid, into an aluminum flask. Okay, and next we titrate this acid solution using standard sodium hydroxide. Okay, until end point we observe permanent color change, and this color change is due to the addition of indicator to this solution because both are similar in color. So to find endpoint, so we put indicator. So indicator will change color once endpoint has been reached. So there are three types of titrymetry: volumetric titrymetry, gravimetric titrymetry, and coulometric titrymetry. So for volumetric titrymetry, uh, uh, this one is establish a quantity of analyte using volume of reagent of non-concentration, okay, concentration that we know, and the knowledge of the stoichiometry of the relation between the reagent and the analyte. So that is volumetric titrymetry. Gravimetric titrymetry will determine the quantity of analyte by measure of mass, okay, because the name comes from gravity. Gravity means mass. Mass of a solution of a known concentration. Whereas coulometric titrymetry arrive at the amount of analyte by measuring the number of coulomb or total charge required when reaction comes to a completion with the analyte. So what is equivalent point? Equivalent point is the point where sufficient titrant has been added to be stoichiometrically equivalent to the amount of analyte. For example, chloride determination. So 50 ml of 0.1 molar silver nitrate solution would be required to completely react with 0.005 mol of sodium chloride. Okay, because balanced chemical reaction is 1 molar to 1 molar. So 50 ml of 0.1 molar means number of mole is mv. Okay, m is 0.1, volume is 50, divide by 1000, we get this 0.005. So 1 to 1. So means number of mole of sodium chloride is 0.005. So that's why you see here 50 ml of 0.1 molar silver nitrate would be required to completely react with 0.005 moles of sodium chloride. So that is equivalence point. Okay, based on our calculation. 50 ml. Yeah. But based on experiment, we call endpoint, and normally endpoint we will use slightly more. Okay, like in the previous example, 50 ml of silver nitrate, but during the experiment, probably we use 50.2 ml of silver nitrate. Okay, that is called endpoint. Okay, the point at which some detection technique tells you that chemical equivalence has been reached. Okay, of course, ideally the endpoint and the equivalence should be the same. Okay, but that is very rare. Okay, that is rare. So the difference between this endpoint here and equivalence point we call as titration error, typically an over titration. So what is primary standard? Primary standard is a high purity compound that serves as a reference material in all volumetric and mass titrymetric methods. Okay, so ideally the titrant solution would be made from a primary standard, and that titrant solution must be of known concentration. Like in the previous example, the figure of hydrochloric acid titrated with sodium hydroxide. So sodium hydroxide is primary standard, the one in the burette, okay, as titrant. And that sodium hydroxide has to be known in terms of concentration, so we must know its concentration. Okay, these are the characteristics of a primary standard. It has to be high purity, okay, stable in the presence of air, means it does not change form in room temperature. For example, you put it on the table, it straight away vaporize. Okay, so that is not a characteristic of a primary standard. It has to be absence of any water of hydration, which might vary with changing humidity and temperature, especially in our country, which is a very humid country. Okay, water hydration means compound which have water hydration in it. For example, sodium sulfate decahydrate. So it has 10 water hydration, 10 molecule of water. So this kind of compound is not suitable as primary standard. Okay, primary standard has to be absence of this, okay, water hydration. It has to dissolve readily, okay, to produce a stable solution in the presence of solvent of choice. Normally we use distilled water or deionized water. It must have relatively large molar mass. This is to minimize weighing error. Next, it has to react rapidly and stoichiometrically with the analyte of interest or the sample. And then lastly, it has to be cheap, although it is not really necessary. Okay, so primary standard for standardization of sodium hydroxide. Okay, so the example given just now between hydrochloric acid, okay, in the figure, hydrochloric acid and sodium hydroxide. So sodium hydroxide is categorized as secondary standard. So secondary standard has to be standardized against a primary standard, which is KHP, potassium acid pentalate. Okay, the primary standard for standardization of hydrochloric acid. So let's say hydrochloric acid is the titrant and sodium hydroxide is a sample. So we have to standardize hydrochloric acid with sodium carbonate. Okay, pure sodium carbonate. Okay, so sodium carbonate here is the primary standard. So secondary standard, normally the characteristic is less pure compared to the primary standard. And it also less stable, but more reactive. And also when it in the solution form, it is more stable compared to primary standard. But still somehow you have to standardize secondary standard with primary standard. So standardization is actually a process in which the concentration of a secondary standard is determined to a high level of accuracy by titration with a primary standard, and I'm sure you have go through this in your practical classes. Okay, next we look at example 15. Okay, to prepare solution with 0.5 molar of chloride from barium chloride dihydrate, how much of the barium chloride dihydrate must be used to prepare 1 liter of solution? Now, first of all, let's assume that barium chloride completely dissociate because this is an ionic compound. Okay, we have metal and also non-metal. So the dissociation of barium chloride will produce barium 2 plus ions and also chloride ion. Okay, balance, we put 2 here. Okay, so ratio is 1 to 2 mole stoichiometrically. Okay, so we are given the molarity of the chloride here. Okay, so which is 0.5 mole per liter. So use the stoichiometric relationship 1 to 2 to find the mole of barium chloride here. Okay, so therefore the answer is 0.25 mole. Okay, once we find mole, okay, we use the molar mass. Okay, so the molar mass of barium chloride dihydrate has been calculated here, 244.2 gram per mole. Using mole and molar mass, we can find mass. Okay, so mass of Barium chloride is 61.1 gram. So we solve this question.